So, you finally got your HF antenna up, your brand new ham radio, and you're excited. So you go on, make a couple QSOs, and then you get someone that starts asking questions, and the QSO sounds something like this. What kind of antenna are you using? You let him know. Okay, that's a very good antenna. Hope you get a lot of good use out of it. And then comes the fatal question. Which way is it radiating? And what you say back sounds something like, I don't know, I put it up, it's facing north-south-ish, and it works, so I don't know exactly what radiating is. This video is going to help take care of that. We're going to talk about baluns, coax, different types of antennas, and how they radiate. So let's get started. Alright, so let's get started. First we're going to talk about some basic types of antennas and how they radiate. So the most common type of an antenna is the dipole. The most second common type would be the vertical, okay? This is going to represent the ground. This is going to represent a tree. And this is going to represent my mast. Sorry about that. Okay. So what we have here for dipole is going to be a length of wire and another length of wire. These lengths of wires are going to be equal length. In the middle you're going to have a center insulator, so the two pieces of wire are going to be connected to some kind of mounting board, and then your coax is going to come up from the ground, running to your shack, and plug in. Now, coax, if you don't know, has two components to it. It actually technically has four, but two conductive components. The one is the center conductor, and the one is the outer shield. So the outer shield gets stripped back and goes to one side, and the center conductor goes to the other. That makes a dipole. The typical way to calculate a dipole is 468 divided by your frequency in megahertz. Sorry, I'm writing this off a little bit sideways. Anyway, 468 divided by frequency in megahertz equals length in feet. So that's my terrible drawing. I'm obviously not going to be a teacher. But yeah, 468 divided by your frequency in megahertz equals your length in feet. That is a dipole. Now, down here, we're going to make a vertical view of this, okay? This is going to be a top view of this antenna. So, your tree is here, and your mast is right here, and these two pieces of wire, looking at it from the top, are running across here. You've got your center feed point, and then your other piece of wire tied off here and here. So this is how this radiates. It radiates looking sort of like this. Okay, that is the main way that a dipole radiates. Now this is a terrible drawing, so I'll do it again over here. Here's your dipole. Here's the center. It radiates something like this. Okay, a very wide figure 8 broadside to the array, which means if you have a dipole antenna up in the air and this is north and this is south, then your antenna is radiating east-west. Okay, now although this and this drawing show that only this part of the antenna is radiating, these ends also radiate, so it's actually a much wider figure 8 than this. The figure 8, it more looks like, you know, it's the size of the antenna. The whole antenna is radiating, but they radiate broadside. So if your antenna is running north-south, your signal is going out east and west. So that gives you an idea of how you can work stations. So if you plan to talk to Europe a lot, you probably want to point your antenna northeast. For most of the United States, northeast is a good way to point your antenna, which means that this is going to face sort of northwest. So north, sorry, I blanked out here, north, south, east and west. Very terrible compass here, but you'd want to put your antenna running like this, because figure 8 broadside is going to point it northeast up towards Europe. So that's a basic concept of dipoles, and that is a very messy dry erase board. So we're going to try and make our vertical presentation a little bit better. But on to vertical antennas now. Alright, time to learn about vertical antennas. Okay, time for vertical. Alright, let's go. Step 1, verticals. This is what a vertical looks like when you buy it from DX Engineering. So, the standard formula for a vertical is you have your coax coming in, and your coax comes into the feed point. I mentioned the center conductor and the outer shield of coax earlier. The outer shield runs to this part of the antenna, which will usually be isolated from this part, and then the center conductor runs to this part. So these swirly things are representing traps, which a lot of verticals have on different spots. They just make the SWR lower on different bands. And then the ground, now if you just bury your vertical in the ground and expect it to work good, you're wrong. It's not going to. Which every vertical needs is radials. Radials are just pieces of wire right below the surface of the ground, running out in all directions. And the more the better. And I'll get to that in a minute. But that's the basic operating theory of a vertical. So how to make a vertical? The easiest way to do this is to use a simple formula very much similar to the one I mentioned in the dipoles a minute ago. This one is half the size of a dipole. It's 240 divided by, frequency in megahertz equals length in feet. That is how you calculate your radials. That's a resonant radial for you right there. So if you're trying to put radials in the ground, which are these in-ground buried wires, then that's the formula you'll use. All these formulas are going to be in the description below, so you can scroll down and I'll have them all titled out so you can get the formulas from below. And how to calculate the length of a vertical, the actual height. Now this is for a single band version. Like I mentioned, some of these will have traps. These change the SWR on certain bands. So what you want to do is, if you want to make it for one band only, and you're just literally taking a piece of copper wire and running it straight up in the air sort of idea, then you use a very similar frequency, but instead of using 240, you use 234. So 240 is for radials, 234 is for verticals. That is for a single band vertical. Multiple bands, you've got to change the length, add capacitors, add coils, stuff like that. Okay, this is not a how to make a vertical video, so we're not going to go into all that. But that's the basic idea. Now, what do radials do? Assuming this is a top view, a two-dimensional top view of your antenna, your vertical is here. That outer shielding we talked about is running into the ground system. What does a ground system do? Well, right now, your antenna, your vertical out in the yard, is stuck into the ground. That ground is absorbing a lot of your signal, and as a result, it's not getting reflected properly. Also, that signal has nowhere to go except into the ground. Big note, the ground is not an antenna. It's not technically conductive. The moisture in the ground and the metal contents are conductive, but the ground is not an antenna. So what radials are going to do is turn the ground into an antenna. You're giving that signal somewhere to go besides the dirt. So different radials are different lengths, and the standard is, this is the just rule of thumb, okay, I'm going to use this box over here for a second. Wavelength, this wavelength, okay, the higher up in frequency, the shorter the wavelength is, okay? So at 1 megahertz, my wavelength might look like this, compared to at 20, my wave might look like that. It gets smaller and smaller. This is not to scale, trust me. 1 megahertz, you have about a 200 meter wavelength. But that's the concept there. So as you increase frequency, as seen by this mathematical equation, your radials are going to get shorter. So ideally you want as many radials as possible. And assuming you buy a vertical instead of build one, you'll probably get a 2-bander version. So the best way to put your radials in is about 1/2 inch in the ground. Just bury them a little bit so you're not going to mow over them, and offset them. So if you've got a 2-band version, say one for 20 meters and one for 10 meters, your 20 meter radial is longer, so go 20, 10, 20, 10, 20, 10, 20, 10, 20, 10, etc., etc. You can keep doing this as much as you want. the more radials, the less ground loss. And, big bonus, the more radials you put, typically the lower SWR you're going to have. I have found that doubling your radials from 2 radials on 40 meters to 4 radials on 40 meters drops my SWR by about 0.2. So it went from 1.4 to 1 to 1.2 to 1, which is a substantial change from almost unusable to perfectly usable. And that's just a little run through on verticals. Hopefully I covered everything. If you got any more questions, leave any questions about antennas that you have in the comments, and I will make a separate video coming back and answering all the antenna questions that you guys have. So the last antenna we're going to talk about is a beam. A beam works the same way as a dipole with its feed point in the center, but it has 2 more elements. So your dipole is here and has a longer element and a smaller element like this. And that gives it directivity. What is directivity? Well, remember a vertical antenna radiates 360 degrees. So it's putting the same amount of power in every single degree, all the way around, 360. A dipole antenna radiates about 260 degrees. 50 degrees off of each side, which is the shaded area here, does not get very much radiation. The radiation pattern is more this area. So a beam antenna, which is antenna number 3 here, this antenna radiates more like this. Let me draw a smaller version here. It radiates more like this. It has a very small radiation in the back, very small off the side. But when you get in the front, it has a much larger radiation. So most of the power is going forward with a little bit to the sides and a medium amount to the back. So you can see most of your power is going in one direction. And these antennas receive in basically the same way that they transmit. So why is this important? I'll show you. Take the standard 100 watts output. Now, we have 3 antennas that we're comparing here, and I'm drawing upside down-ish, so forgive me if this looks terrible. So, this is a relative example. This is not totally accurate, but it's going to kind of get the point of radiation across. So don't go around HF saying some expert taught me this is how it works, because it's not 100% accurate, but the theory is correct. So how this works is if we have 360 degrees of radiation, then, I'm sorry, not 366, 360. We have 360 degrees of radiation here, and this is about 260 for the dipole, and say we only have 120 on the, what am I trying to think here? On the beam antenna. Why couldn't I think of what it was called? I don't know. But anyway, so the equation here, we're going to divide this. So 100 divided by 360. If you passed your general to be on HF using these antennas, you should know that this number, the equation here is this x is going to be a lot more than this z, or I'm sorry, y, we'll put y, and this will be z, okay? X is going to be a smaller number than y, which is going to be a smaller number than z. Now this is important because 100 divided by 360, for some reason I can't just think of that in my head right now. I'm going to try and kind of sit here and think it out a minute, but it's going to be 0. It's going to be roughly 0. I guess 0.2, roughly. This is not accurate. I'm just kind of putting a number there to fill in the gap because my brain is lapsing. But I guess that's what I get for working out in the heat and then coming and make a video right away in July. But 0.2 watts, we'll just say. So 0.2 is the equation here. That means in every degree of radiation, which is a complete circle, it's putting out 0.2 watts times 360 is going to equal 100. Obviously, that's not quite correct, but it's an example. So here, we're going to have the same thing. We have now
on a dipole, only 260 degrees of radiation. That's going to be 100 degrees less. So now we can say we have 0.35 watts going out in every of the major radiating direction, because that same 100 watts has to get dissipated in less and less degrees. And that's why a beam is effective, because now we're down to 120 degrees. We're getting almost 1 watt per degree of radiation. And this is not perfectly accurate, but this really just kind of lightens it up a little bit. Hopefully this makes sense, okay? If you get a calculator and do the math for yourself, it'll make a lot more sense. So hopefully that explains the beam theory for you. But how does a beam work? A beam has a driven element, and that is the dipole. It's the same standard 248 divided by frequency. Now, that can be pretty big on HF for a beam. So a lot of times there's little traps or stuff in here to make it shorter. But you'll have your driven element. Then there will be a metal pole, a boom, along it. The back element is longer than this element. This acts as a reflector, and when this radiates in that standard figure 8 pattern that we're talking about, that signal is getting shot back forward. So it's kind of sending that signal back up. Up here, there's a shorter element, and this takes the signal and draws it out into the arrow that it is going to be radiating on. So you can kind of look at your beam antenna as a big arrow, where the boom is the line down the middle, and you can trace these out to get the arrow. So that's sort of the technical how-to of a beam. So that kind of hopefully explains the radiation pattern, and I will go ahead right here. I'm going to insert a picture after I'm finished talking of the different radiation patterns. And hopefully that makes a little more sense to you now instead of my sloppy drawings. So now I'm going to talk about a little bit about SWR, and we'll let you go because this video is getting kind of long. Alright, so the last thing we're going to talk about is SWR. And SWR, as you probably know, is bad for your radio. Nobody likes SWR. This is your radio, your brand new, expensive radio with a whole bunch of buttons and a nice touch screen and a bunch of coax running up to your antenna. The problem is, inside this radio, there are little finals inside the back of this radio where the antenna comes in, and where your signal is processed, there's little finals in there. And that's kind of where your signal is processed and it's sent out to go be radiated to the world. These can be damaged if your SWR is higher than approximately 1.6 continuously. So that's my picky number. I try and always keep my antennas below 1.3. Now, some people say as long as it's below 1.9 you're okay, but I try and keep it around 1.3. What is SWR? SWR is a ratio, standing wave ratio. Standing wave is just reflected wattage. So a 1:1 SWR is 50 ohms to 50 ohms. This number represents the ohms of your antenna, and this number represents the ohms of your radio. That is why this number is always 1. 50 ohms is considered 1. On this side of the ratio, you have more numbers. If you get a 2:1, that means your antenna is 100 ohms, not 50. That's a 2:1 SWR. A 1.5:1 SWR is 75 ohms. So if you made an antenna that was perfectly resonant for 75 ohms and fed it with 75 ohm coax into the back of your radio, you would have a 1.5:1 SWR. Now, that's okay. 75 ohms going into a 50 ohm radio isn't going to hurt anything as long as you don't operate for an extended period of time. Ideally, you should probably keep it at 60 ohms or less, which is around a 1.3. So all you have to do is consider at 50 ohms to whatever number. So your ohms is, you can consider at 50. Now 75 to 50 would be a 75 ohm feed line or antenna going into a 50 ohm coax. And you can obviously just divide this and reduce this to be 1.5 to 1. So you can easily reduce it. So all SWR is a ratio of 50 ohms antenna impedance to whatever the impedance of your antenna is. So as long as you have some math or some scratch paper or a calculator handy, you can instantly figure out what the impedance of your antenna is based on this number. So if I say, okay, I have a 2-to-1 SWR, and we know that point X, which is the radio, so let's just make this a little more easier to understand. Point A and point R. Point A is your antenna ohmage, and point R is your radio ohmage. We know that R is always going to be 50 ohms. So we can deduct from a 2-to-1 SWR that this is 2 times that, which lets us know that our antenna has a 100 ohm impedance. So there is a couple ways to fix this, and the first easiest one is tuning your antenna. But if you don't want to tune your antenna, or if other factors come into play, they make something that can help you with this. If you put some wire in the air, and right here, the SWR is 2-to-1, meaning that this is 100 ohms, and you have 50 ohm coax coming up, well, that's not going to work. You're going to have some SWR problems. They sell a balun. A balun is a feed point type of thing, and this is just a crude drawing of one. They come in a lot of different ways. They sell a balun. Now what a balun is it divides SWR. Now the way the baluns are rated is 1-to-1, 2-to-1, 4-to-1, 6-to-1, 9-to-1. So a 2-to-1 balun, don't be scared of it, because it doesn't mean it's going to have a 2-to-1 SWR. What that means is that if the incoming wires that you hook up to it have 100 ohms, it's going to downstep it to 50. A 6-to-1 would mean that it would take 300 ohms and convert it to 50. A 4-to-1 would be 200 ohms converted to 50. So this is the exact same theory as the SWR, the antenna to radio factor, but now it's going to be rewritten as wire to coax factor. And you have to do this in your head. That is how they're rated. So if you have 75 ohms impedance and you want to make it 50, you'd get a 1.5-to-1 SWR balun. So that doesn't mean that's what the SWR is that they're going to have. It just means that's what it's going to convert it to. So if you have an antenna that has a steady 2-to-1 SWR, now this could be for several reasons. It might not be that it's 100 ohms, but if you get an antenna that has a steady 100 ohms across your whole band, then you can just get a 2-to-1 balun that'll downstep it and divide it by 2, resulting in a perfect 50 ohm match. So that's sort of how baluns work. And hopefully I gave you a quick rundown of everything you need to know about antenna theory for the next couple months. 73s, thank you for watching. If you've got any more antenna questions, post them below and I'll make a separate video answering all the antenna questions that you have.